Hi, in this video we're going to prove some property to do with the squares of consecutive odd or even integers. Now in the previous video we showed how we could represent consecutive odd integers. Remember that any odd integer could be represented as, say, like 2n plus 1. Why? Because any odd number is one more than a multiple of 2. Now 2 times n, where n is any whole number, 2 times any whole number will be even, and even plus 1 will give you any possible odd number. And then we said if we wanted the next odd integer, if I had, say, 7, how do you find the next odd integer? Well, you'd add 2. 7 plus 2 is 9. That gets you the next odd number. So if we add 2 to this, 1 plus 2 is 3, so we get the next odd integer after that. Now, okay, we want to prove algebraically that the difference of the squares of two consecutive odd integers. So if we make the two odd integers, well, the 2n plus 3 and the 2n plus 1. Now, the reason I'm putting the bigger one first, the 2n plus 3, is because we're going to find the difference of them. And when you do a difference, you want to do the bigger number minus the smaller number. But it's a difference of the squares. So we're going to square each and then find the difference of them, the subtraction of them, doing the bigger square minus the smaller square. We need to show this is always divisible by 8. We'll see how to do that in a second. But firstly, we should just expand these brackets. So let's just write each bracket out twice, because when you square a bracket, you just times it by itself. And let's just expand this out. So we do each thing in the first bracket times each thing in the second. We're going to do 2n times the 2n, which is 4n squared. We're going to do the 2n times the 3, which is 6n. I'm going to do the 3 times the 2n, which is 6n again, and the 3 times the 3 is 9. Now, remember, when you subtract anything that's being expanded, you should put it in a bracket first. We'll see why, to do with making sure we don't make sign errors. Let's expand this. 2n times 2n is 4n squared. 2n times 1 is 2n. 1 times 2n is 2n. And 1 times 1 is 1. And now, let's just tidy up a bit. We've got 4n squared. We've got 6 lots of n plus another 6 lots of n. That's 12 lots of n plus 9. Let's tidy up in the bracket as well. We've got 4n squared. 2n plus 2n is plus 4n, and we've got the plus 1. Now, the reason I put that bracket there is because you're not just subtracting the 4n squared, you're subtracting every term in this bracket. And that's basically going to reverse the signs of these. So the 4n squared becomes minus 4n squared, the plus 4n becomes minus 4n, and the plus 1 becomes minus 1. So let's do that. Minus 4n squared, minus 4n, and minus 1. And let's just simplify by collecting like terms. The 4n squared minus 4n squared cancels. We've got the 12 lots of n minus 4 lots of n, which is 8 lots of n. And then we've got 9 minus 1, which is plus 8. Now, we want to show this is always divisible by 8. And then remember, the way we do that, to show something's a multiple of 8, is just factorize the 8 out. So if we factorize the 8 out, we've got 8 times, well, what? So 8 times what is 8n? It's n. And 8 times what is plus 8, which is plus 1. And basically, 8 times any whole number is guaranteed to be a multiple of 8, guaranteed to be divisible by 8. And therefore, we're done. Now, because we're trying to prove this is always divisible by 8, you should probably, just to be on the safe side, state the thing that you were trying to prove, that it's always divisible by 8. So let's make that explicit. You can say, which is always divisible by 8. And that completes our proof.